Alright, hi everyone. This is video 2 for our Friday, May 16th lecture. So for this video, we'll just be going over section 12.3. So the first thing that we're going to be talking about is attractive forces. So the first one is intramolecular forces, which are bonding forces. So these are things like in hydrochloric acid, which is HCl. It's the actual force that keeps the H plus and the Cl minus bonded together. So the chemical behavior of each phase is the same, which is basically saying that HCl will react the same way in a solid, liquid, or gas form. Another example, H2O, you always have two H's bonded to an O, and it's those forces that keep those bonds together. The other type of force is intermolecular force, which we're going to be expanding upon, and these are non-bonding forces. So these would be forces between an H2O molecule and another H2O molecule, or say an HCl molecule and an H2O molecule. So it's between two molecules. And this changes the physical behavior of each phase. So the strength of the forces changes in the solid, liquid, and gas. So, like I said, it's between two particles or two molecules. So the attraction of those two molecules with partial charges, or the attraction between ions and molecules. So we'll get into there are different names for intermolecular forces based on if you have a partial charge, if it's an ion, or if it's just a nonpolar molecule. So one of the interesting things is that these intermolecular forces are pretty weak compared to bonding forces. So if we think about bonding forces, keeping H bonded to O, bonded to another H in water, it's really, really hard to break those forces compared to things like going from a liquid phase to a gas phase. We only have to put in so much energy in order to get it to the gas phase. When we go from the liquid to the gas phase, we're actually breaking apart those intermolecular forces and overcoming those forces that are keeping things together in the liquid phase. You have to put in a lot more energy to actually break the bonds. So here's a table just comparing different kinds of bonding and non-bonding forces. So we have ionic, which is usually between a cation, which is positively charged, and an anion, negatively charged. Then we have covalent forces, and this is with usually two nonmetals, so they share electrons. So that would be like H2 or O2. And we have metallic forces, so these are cations, and they have delocalized electrons, which is kind of an electron cloud. So you can think about ionic as a metal and a nonmetal. Covalent is two nonmetals, and metallic is obviously a metal. So these three types of forces are all bonding forces. So they're intramolecular forces. Let's move on to intermolecular forces. So these are the non-bonding forces. So you have a variety here. The first one is ion dipole. And these pictures should help you kind of try to visualize what that actually looks like. So the dotted line is the force. So here we have an ion, and we have a dipole. So a dipole means that it's going to have sort of a negative side and a positive side. So if you look over here at the example, Na plus is the ion, and H2O right here, so we have an O bonded to H, O bonded to another H. This is a dipole because it's a polar molecule. So the H's are the positive end, and the O is the negative end that's going to be attracted to the sodium ion. The next one is hydrogen bonding, and with this, it's a force that is between the hydrogen of one molecule to either a nitrogen, oxygen, or fluorine on another molecule. So nitrogen, oxygen, and fluorine have a high electronegativity, so that positive H is going to be attracted to that slightly negative nitrogen, oxygen, or fluorine. Next, we have dipole-dipole, which is just the interaction between two polar molecules. Then we have ion-induced dipole. So induced dipole means that it's a molecule that's usually nonpolar. In this example, we have O2. But when it's near something like an ion, it's going to kind of temporarily slush all of its electrons to one side so that it's more negative on that side. So you can kind of think about this in the bathtub when you were little and the water all sloshed to one side, and then eventually it went back to normal. So that's what happens to nonpolar molecules. So when it's near this ion, it's thinking, oh, hey, well, you're positive. I kind of want to be attracted to you, so it sloshes all of its electrons to this side, making it negative, and then all on this side is temporarily positive, so they are attracted to each other. Now this obviously won't be as strong because it can just slosh all of its electrons back and be nonpolar. Here's another example, dipole-induced dipole. So this is with a polar and a nonpolar molecule. And the polar molecule can do the same thing. It can make that nonpolar molecule become polarized by sloshing the electrons. Now it's going to slosh the electrons to this side, because here you can see for HCl, it's going to have a negative side on here, so it wants a positive side for ClCl. The last type is dispersion, which is also called London forces, and that's between two nonpolar molecules. It's also important to note that dispersion forces are actually present in all cases. So how do you actually determine what intermolecular forces there are? So I made this chart. Again, don't really like the one in the textbook. So here, the first thing to know is, are there ions? If there are, you have to say, are there only ions? Maybe there are ions in a polar molecule. Maybe it's ions in a nonpolar molecule. If there are no ions, you have to ask, are there only nonpolar molecules? Are there nonpolar and polar mixed together? Or are there only polar molecules? And if there are only polar molecules, could there be hydrogen bonding? So I hope this chart will be a little bit simplified. Okay, question 7. We'll use one of the PRS that I was hoping to do. So here, what is the strongest interparticle force in CH3F? Ion-ion, ion-dipole, hydrogen bonding, dipole-dipole, or dispersion forces? Okay, question 8. This one's a little bit different molecule. What is the strongest interparticle force in ethanol in water? Ion-ion, ion-dipole, hydrogen bonding, dipole-dipole, and dispersion forces. Okay, now we're going to talk about hydrogen bonding and boiling point. So hydrogen bonding, we know, is stronger than dispersion forces. And the stronger intermolecular forces that you have, you need more energy to actually go from the liquid phase to the gas phase. So this means you have a higher boiling point. So if you look over here, everything from here over is pretty much all dispersion forces. And you'll see they have relatively similar boiling points. They get a little bit, they get a little bit bigger as we go across the period. But you'll notice that these over here do not follow the same trend. That's because they have hydrogen bonding. So that's why they have a much higher boiling point, because those hydrogen bond forces are keeping those particles together. They don't want to leave the liquid phase just yet. So we talked a little bit about how in a nonpolar molecule, you can have the sort of distortion of the electron cloud, this sloshing of electrons. And that is called polarizability. So it's how easily an electron cloud can be distorted, or the electrons slosh to one side. So it's a temporary dipole. Like I said, it can go back to being normal and nonpolar. And for a polar molecule, it can actually also be polarized, and it basically enhances the dipole that is already there. So it's making a negative side more negative and the positive side more positive. And there are some of these trends that can be seen in the periodic table. So we're going to go back to dispersion forces and talk a little bit more about them. So dispersion forces happen when the atoms or particles are so close together that they form an instantaneous dipole in one atom, and that induces a dipole in another. So it's kind of like a domino effect. If one of them has electrons that slosh one side, that's going to influence the polarization of the particle that's next to it. So this contributes to the energy of attraction in all substances. So if you remember before in our chart, I said that dispersion forces are always present in all cases. So the relative strength depends on the number of electrons, and it correlates with molar mass. But dispersion forces are usually the weakest of all of the forces. The other thing to keep in mind is that there is an effect of molecular shape. So if you have two things that are the same molar mass, one of them is probably going to be more spread out, and so you're going to have more points at which dispersion forces can act, which means it's going to have a higher boiling point. And we'll talk a little bit about that later. Actually, in the next slide. So if we look at N-pentane here on the left and neopentane here on the right, if you count up all of the carbons and hydrogens, they're the same in both of them. So they have the same molecular mass, but you can see they have really different shapes and structures. So N-pentane is a lot more spread out. It's just a single carbon chain. And neopentane on the right is more compact. So if you have something that's more spread out, there's going to be more points at which you can have dispersion forces, so it's going to have a higher boiling point. So for question 9, I'd like you to try to come up with another example of two molecules that are the same molar mass but have a different structure, and write down what their different boiling points are. So you're going to draw the structure, give the name, and give the boiling point for the two compounds. So that is 9. Okay, so now I'd like you to take a few minutes and reflect on 12.3. You can write a summary or draw pictures or symbols, things like that. And then you can follow up with video 3 for our lecture for May 16th.